All right. Good evening. Am I audible? Hello. Can you guys hear me? Yes. Can you hear me or not? You can type in chat if you don't want to speak. All right. So this is the first problem solving session on information theory course offered on NPTEL. I am Sachin from the Indian Institute of Science and I will be conducting only problem solving sessions. If there are any other queries, of course you can ask questions or if you don't understand some topics in the theoretical in the recordings that are shared with you each week. But other than that, any logistical questions like mistakes in the grading, the mistakes in the questions in the assignments, deadlines, all such stuff has nothing to do with me. You guys will have to go to the Gmail group. You must have been, you must have the link for that, where you can ask questions, and there the TAs who are responsible for grading and all, who work directly under the professor, those guys will take care of that type of technical stuff. So my main job is to solve assignment questions from previous years, and basically I need to solve 10 questions. They will be very similar to the assignment questions that you have for this year. So if you can understand how to solve the previous year questions, you should be able to solve this year's assignment. Other than that, everything else is up to me. So there are only 10 questions in each assignment, so it won't take too much time. But still, this is a 2 hour slot, so unless people have doubts, I'll probably solve a few problems from the textbook. Thomas cover and Joy Thomas, or if there is some concept you would like me to explain, I can do that. But first, we will solve a few questions from previous year assignments. It would be helpful to you if you have a notebook and a pen with you and you can solve the problem yourself. You can try to solve it yourself and then check if your solution matches the correct answer. Okay, the first question is, let the probability mass function PMF denoted by Px of x, so the random variable is x, taking values small x from some alphabet script x of a discrete random variable capital X be positive at x equals -1, 0, 1 and 0 elsewhere. If the probability that x equals 0 is 1/4, Then what is the expected value or the expectation e of x square? We have four options. Is it 0? Is it a half? Is it 3/4? Or is it 3? I'll give you 2 minutes. You can try it out. Then I'll come back and give you the answer. Note that we are using base 2 for all logarithms. All right, 2 minutes are up. So here's the solution for this question. What they have asked you is to find the expected value of x squared. So expectation is taken only for random variables. Here, x square is a random variable. I could give it a different name. So I will call x square as a random variable y. So what values will x square take? Where x takes only the values -1, 0, and 1. So -1 square is 1 and 1 square is also 1. So x square takes only the values 0 and 1. So y is a discrete random variable taking only two values, 0 and 1. Now, if you want to find the expected value of y, we need to know the probability distribution of the variable y. That is, what is the probability that y takes the value 0 and what is the probability that y takes the value 1. So y is probability that y is 0. When is y 0? Y is 0 only when x is 0. So this probability is equal to the probability that x is 0, which is 1/4. This is given. Then what is the probability that y takes the value 1? This is the probability that x is either -1 or x is equal to 1. In both cases, x squared is y, which is 1. Since the sum of the probabilities of any distribution PMF must be 1, and P of x0, x is equal to 0 is 1/4. P of x is equal to -1 plus P of x is equal to 1 is 1 minus P of x equals 0, which is 1 minus 1/4, which is 3/4. Now, the expected value of a random variable y is nothing but the summation over all values y, probability that y is equal to y, into y. So since in our case small y takes only two values 0 and 1, this is 0 times the probability capital Y is equal to 0 plus 1 times the probability capital Y is equal to 1. The first term goes to 0, second term is 1 times 3/4, which is 3/4. So the correct answer is option C. Any doubt in this? It was very simple, but if you have any point of confusion, you can ask. No need to feel shy or embarrassed. You can ask any type of questions. It doesn't have to be very complex. Even simple questions are fine. I'll answer them. Okay, looks like there's no problem. And we'll go to the next question then. Question number 2. For the same discrete random variable as specified in question 1, if p of x equals 0 is 1/4, and if expectation e of x is also 1/4, what are the values of p of x equals -1 and p of x equals 1? Again, you have four options. X equals 1 has probability half and x equals -1 has probability 1/4. The second option is p of x equals 1 is 3/8. So p of x equals -1 is also 3/8. Third option says p of x equals 1 is 1/8. P of x equals -1 is 5/8. Fourth option says p of x equals 1 is 5/8. P of x equals -1 is 1/8. Again, I'll give you 2 minutes. You can try to solve it yourself. Then I'll come back and give you the solution. Alright, here's the method to solve this. They've given that p of x equals x equals 0 is 1/4 and e of x is also 1/4. From this we can get two equations. The first equation we can get uh, by using the fact that the sum of the probabilities of all three values must be 1. So p of x equals 0 plus p of x equals 1 plus p of x equals minus 1 must be equal to 1. So from this we can get p of x equals 1 plus p of x equals minus 1 is 1 minus p of x equals 0, which is 3/4. The second equation is from the expected value e of x is 1/4. So using the formula for the expected value. So here I had written it for y, the same thing for x. Capital Y is replaced by capital X and small y you can replace by small x. But then e of x is nothing but 0 times probability x equals 0 plus 1 times probability x equals 1 plus minus 1 times probability x is equal to minus 1, which is again 1/4. This term goes to 0. Let me call this equation 1. So now you get p of x equals 1 minus p of x equals minus 1 is 1/4. Add the two equations and you get 2 times p of x equals 1 is 1. So the probability that x equals 1 is half, and substitute the value in any one of the equations. From that you will get half plus p of x equals minus 1 is 3/4, which implies p of x equals minus 1 is 1/4. So half and 1/4, which is option A. Let's move on to question number 3. Let x be a discrete random variable with entropy h of x, which of the following statements is true. There are four statements. First one says that h of 5x is equal to h of x. Second one says h of 5x is equal to 5h of x. Third statement says h of 5x is equal to 1 over 5h of x. And fourth statement says h of 5x is h of x plus log 5. I'll give you 2 minutes to think about it. Then I'll come back and give you the solution. All right. The solution. So let's say y is a new random variable which is equal to 5 times x. Oh, x. So the PMF, probability mass function of y, is the same as the PMF of 5x. And why is that? That is because y equals 5x is a one-to-one function or correspondence. And the entropy only depends on the probability mass function, not on the random variable itself. Regardless of what you call the random variable, if two different random variables have the same probability distribution, then they will have the same entropy. So the entropy depends is a function of or depends only on the probability distribution, which in the case of discrete random variables is given by the probability mass function. Therefore, h of 5x is equal to h of x, which is option A. If you are not convinced, we can do an example. So, an example, we can take the example, the random variable from the first question or the second question, where from question 2, x um, takes values from -1, 0, 1. Probability of x is x equals 0 was half, it was 1/4. Probability that x equals 1 was half, and probability that x is equal to -1 was 1/4. Then h of x is minus summation px of x log px of x, or all x in script x. So this set we call script x, just a notation. It should be the support of px, but here all the support is script x. All other values have zero probability. That's what we saw in the first question. So this will be equal to minus 1/4 log 4 plus half log 2 plus 1/4 log 4, which is log 4 to the base 2 is 2. So this half plus log 2 to the base 2 is 1 half. This is also half, which is minus 1.5 bits. So the random variable y is equal to 5x will take values from, if x is -1, it's y is -5, x is 0, y is 5, and x is 5, y is 5. And distribution probability y is -5 is nothing but probability that x is -1, which is 1/4. And probability y is 0 is the probability that x is 0, which is a half. Sorry, it was also a 1/4. And probability y is 1, y is 5 is equal to the probability that x is equal to 1, which is a half. Now h of y is summation probability y is equal to y log p of y is equal to y belongs to, so this is called script y, which is again minus 1/4 log 4 plus half log 2 plus 1/4 log 4, which is minus 3/2 bits. So in this way, if you have a random variable x, let me write that down. If x is a discrete random variable with entropy h of x, and y is a one-to-one function of x, then h of y equals h of x. If it's not a one-to-one function, then the entropy need not be equal. And you can see that by going back to the first question, where y is equal to x squared, it was not one-to-one. So When x was minus 1, y was 1. When x is plus 1, y is 1 because y is equal to x squared. So the probability distribution of y in the first question is P of y equals 0 is 1/4 and P of y is equal to 1 is 3/4. The entropy, uh, this is not true in general if G is not 1 to 1. Example, y is equal to x squared from Q1 where P of y equals 0 was 1/4 and P of y equals 1 was 3/4. H of y is, sorry, I think I was writing negative signs here. There's no negative sign. I took the reciprocal of 1 over 4. So it's minus 1 over 4 log of 1 over 4, which is equal to 1 over 4 log 4. So by taking reciprocal of the probability, I remove the minus sign. So its entropy is always positive. So in this case, when y is equal to x squared, the entropy is 1 over 4 log 4 plus 3 over 4 log 4 over 3, which is 0.5 plus 0.752 log 4 minus log 3. Log 4 is 2 minus log 3 base 2. What is log 3 base 2? This is 1.585. So this will be 0.811 bits, right? Which is less than 1.5 bits that we had for x. So if y is not a one-to-one function of x, then its entropy need not be equal to x. If y is a one-to-one function of x, its entropy is equal to the entropy of x. Next is question 4. Let there be 3 random variables x, y, and z such that p of xy given z is equal to p of x given z, p of y given z. That is, x and y are conditionally independent given z. What is I of xy given z? The four options are 0, I of xx given z, I of y given z, and d is none of the above. I'll give you 2 minutes to figure that out and come back and give you the solution. Okay, I hope you gave it a shot. So there's this thing I of xy given z is equal to I of yx given z. It's completely symmetric with respect to x and y. So if the answer actually was option B or C, I of xx given z or I of yy given z, then both should have been true. So just from the symmetry arguments, you could say either both B and C are true or both B and C are false. Since it's a single option question, you could rule out B and C just like that. But if you work it out, uh, it's this. Since x and y are conditionally independent given z, from the lectures you must have seen that if x and y are conditionally independent given z, then h of x given yz is equal to h of x given z. So h of x given z minus h of x given yz is 0. But this quantity h of x given z minus h of x given yz is I of xy given z. So that is 0. So if x and y are conditionally independent given z, then the mutual information between x and y given z is 0. Yes, so uh, this quantity I of xy given z, that's defined by definition as h of x given z minus h of x given yz, right? And when x and y are conditionally independent given z, h of x given yz is equal to h of x given z because x does not depend on what y is. No. Uh, how do you say it's equal to h of y given z? then if you but in see information is always a difference between two quantities. So if you write it in terms of y, you can also write it as h of y given z minus h of y given xz. So in that case, since x and y are independent, this will be h of y given z minus h of y given z. H of y given xz will be equal to h of y given z. Again, it will be equal to 0. So if x and y are mutually independent, h of x given y is not 0. H of x given y is h of x. And h of y given x is not 0. It's h of y is equal to h of y. H of y given x is equal to h of y if x and y are independent. The mutual information between them is 0. See, what is mutual information? Suppose you are sending a message. You are speaking into your phone. Right now, I am speaking into the microphone that is being transmitted over a channel, and there might be noise in the channel which will change the uh, what you're actually receiving. But still, because uh, what you receive is the sum of the noise and what I transmitted, there will be some information about what I transmitted in the received signal. So there is some information about X that I am sending to you in Y, if Y actually depends on X. So by observing Y, you are actually reducing the uncertainty in X. If even if you get a garbled, jumbled up version of what I am telling you, if there is some noise, you will get a distorted version of my speech. But if there is some relation to what I am still saying, you will still be able to understand the bits and pieces of what I am telling you, right? So there will still be some information between what I sent and what you received. But if what you received is completely independent of what I am sending you or what I am telling you, then by hearing the received words, you don't really know what was actually sent. So the uncertainty in what I am saying is not really reduced. If you still don't understand, you could write out the expression for what these quantities are. So h of uh, x given yz, you could write it out as a summation of probabilities and verify that h of x given yz is equal to h of x given z if x and y are conditionally independent. Do you still have a doubt? What exactly is your doubt? Are you sure? I mean, you understood, right? Okay. See, let me check. He did prove that conditioning reduces entropy, right? Let me check the notes. So he did the proof for y h of x given y is less than or equal to h of x, right? And in that proof, he gave you the equality condition when this will be equal. So h of with equality, if and only if x and y are independent, right? You understood that part, no? Why they have to be independent in the proof? Then if you have two random variables x and y, the mutual information is defined as the reduction in the entropy, that is h of x minus h of x given y. By observing a random variable y, how much entropy can be reduced in the uncertainty in the random variable x. So that's the mutual information between x and y. So if x and y are independent, then h of x given y is equal to h of x. So this is h of x minus h of x, which is equal to 0, right? So the only difference here is there is an additional conditioning. They're also conditioning on z, but that doesn't change any of these inequalities. So the proof for that usually nobody does it because it will be very cumbersome. It's very notation is very there's too many things going on when you write that. So h of x given yz is actually average over all values of z, pz of z, h of x given y comma z is equal to z, right? Over all values in or all z values in support of pz. That's how it is defined. H of x given yz. Then further, this h of x given y comma z is equal to z is again defined as summation negative of summation over all xy in some support of p of xy given z, x comma y given z, log of p of x given yz, x given y, x given y comma z. So now you have, I'll not write down the supports, I'll write down the expression. Summation p xy given z of x comma y given z. The definition of conditional independence says that this is equal to p of x given z of x given z into p of y given z of y given z. And log of this thing you can write as p of xy given z of xy given z divided by pz of z. Okay. Then h of x given z is the summation over all z, pz of z. H of x given z is equal to z, which is again summation. This is minus summation over all x. P of x given z log p of x given z. So you have to do some more manipulation in the above term, and you will be able to eliminate the y given z parts. They'll sum to 1. Okay. So what I'll do is, for now, I'll keep it as it is. And in next class, if you attend, I will write this down exactly. I'll do the manipulations and tell you the proof. Okay. But you can prove from this that if x and y are independent given z, then h of x given yz is equal to h of x given z. Once you have that proof, by definition, I of xy given z is equal to h of x given z minus h of x given yz. Since the two quantities are equal, I of xy given z is 0. Okay. Usually, the proofs for the conditioning is skipped in most of the books because they're just notationally very cumbersome. It takes up too much space, and the proof follows in a similar way to the proof without conditioning. So you already have this h of x given y less than or equal to h of x with equality if and only if x and y are independent. So what you're doing is giving an additional conditioning which doesn't really change. The structure of the proof is the same, but you'll have to write out a lot more steps. Okay, so the answer was 0, option A. Next is question 5, which is a straightforward question. Which of the following statements is true? I of xy given z is equal to h of x given z minus h of x given yz. Option B is I of x given, sorry, I of xy given z is equal to h of y given z minus h of y given xz. Option C is h of, sorry, I of xy given z is equal to h of x given z plus h of y given z minus h of xy given z. Option D is all of the above. And the solution is just option D, because this is just by definition A and B are, A is the definition for h of x, h of I of xy given z. So I of xy given z is equal to h of x given z minus h of x given yz. That's just the definition. Second option is true because the mutual information is symmetric. So uh, I of xy given z is equal to I of yx given z. So you can write it as h of y given z minus h of y given xz also. Option A is true by definition. Option B is true by symmetry because I of xy given z equals I of yx given z. Option C, just a little bit of manipulation. We can write h of xy given z using the chain rule as h of x given z plus h of y given xz. So you could write h of y given xz as h of xy given z minus h of x given z, and substitute in option B. So in option B you have a h of y given z minus h of x y given xz. So in place of h of y given xz, you write down the RHS of the above equation. So you get y of xy given z is equal to h of y given z minus h of xy given z plus h of x given z. So that is option C, h of x given z plus h of y given z minus h of xy given z. So all the options are equivalent definitions, and depending on what information you have, you can use them. So depending on the problem, of course, this is just theory, but in real life, you can't really decide what values you get, whether you know the entropy of x given z or y given z or y given xz, which is more convenient to measure or which is more convenient to calculate. So depending on the application, you can use any of the definitions and you'll get the same quantity, which is the mutual information between x and y condition conditioned on the variable z. Then we have question 6 for two random variables x and y, of course discrete. H of x base 2 is 5, h of y base e is 4, and h of xy base 10 is 3. What is I of xy base 2? We can round the answer to one decimal place. Option A is 0.2, B is 0.8, C is 6, and D is 12. And for your convenience, I'll give you the values. Log e base 2 is 1.4427. Log 10 base 2 is 3.32. So using that, you can find I of xy in bits. So basically, you have to convert h of y and h of xy from base e and base 10 to base 2 respectively, and then use the formula for I of xy, which is h of x plus h of y minus h of xy, which we saw earlier in question number 5. Only thing is it was conditioned on z. Here there's no conditioning. I'll give you 2 minutes to solve this and then I'll come back and give you the answer. Okay, there's a solution, and we use the formula HB of x is log A base B times HA of x. So H2 of y is log E base 2 HE of y, which is 1.4427 into HE of y was 4, so this is 5.77. H2 of xy is given in terms of base 10, so log 10 base 2 times h of xy to base 10, which was 3.32 times 3, which is 9.96. So I of xy is h2 of x plus h2 of y minus h2 of xy, which is 5 plus 5.77 minus 9.96, which is 0.81. That is option B. Next is question 7. Let x, y, z have the following joint distribution. What is h of xy given z equals to, and I'll give you the distribution. So this is the joint distribution, not the conditional distribution. So, and z takes four different values, 1, 2, 3, or 4. And xy take four different values, 0, 0, 0, 1, 1, 0, and 1, 1. This is the distribution. And the options are 1 over 4, 1 over 2, 3 halves, and 1. So I'll give you 2 minutes. I'll give you 3 minutes for this. You have to find h of xy given z is equal to 2. So if it's a bit confusing, you can simply take xy as some random variable w. So you can just write w equals xy. So what you are finding is h of w given z is equal to 2. So you can treat um, joint random variable, a random vector, so x and y jointly as one random variable, and you'll still get the same results. Because the entropy depends only on the distribution and not the name of the random variable that you're given. Here's how you solve this. They are asking for h of xy given z equals 2, which, so h of xy given z equals z is defined as probability of xy is xy given z log of 1 over, you could write this as probability x comma y given z log 1 over p of xy given z. Okay, one point that you shouldn't get confused here is when we write I of xy given z or p of xy given z, it's not, if you write I of xy given z, it's not the mutual information between x and y given z. It's not this. That's not what it means. Here also, p of xy given z is not p of x comma y given z. This is not a single entity. And this summation is carried over all values of x and y. So what's z, where z is a fixed value. Here z is equal to small z is equal to 2. So h of xy given z equals 2 is summation over all xy. P of xy given 2 log 1 over p of xy given 2. What we really mean when we write p of xy given z is probability that xy takes the value, the random variables x and y take the value x and small y, given that random variable z takes the value small z, which can be written, which again is defined as p of xyz is equal to xyz divided by p of z is equal to small z. That's just from probability. That's the definition of conditional probability. Now you have p of xyz is equal to small xyz for every possible value of small x, small y, and small z that's given in the table. So this entry is p of 0, 0, 1. This entry is p of 0, 0, 2. So you have that, but we don't have p of z is equal to 2. It's not given in the table. So what you have to do is you have to marginalize. And by that we mean you have to go to the column z is equal to 2 and the probability that z is equal to 2 is the sum of these probabilities in the column z is equal to 2. So probability that z is equal to z is summation over all possible values of xy, probability of xy and z. So probability that z is equal to 2 is equal to summation of all xy, probability of xy comma 2, which is all these entries. Xy can take 0, 0, 0, 1, 1, 0 or 1, 1. Z can only take 2. So sum of all those entries in others p of 0, 0, 2 plus p of 0, 1, 2 plus p of 1, 0, 2 plus p of 1, 1, 2, which is equal to 1 over 16 plus 1 over 8 plus 1 over 16 plus 0, which is 1 over 4. Now putting that back into our formula, h of xy given z equals to, okay, so now we have to find out p of xy given z equals to for all xy. So p of 0, 0 given z equals to is p of 0, 0, 2 divided by p of z equals to. So 0, 0, 2 is this 1 over 16 divided by p of z equals to is 1 fourth. So it is 1 over 16 divided by 1 over 4, which is 1 fourth. So in essence, what you are doing is the sum of the entries in the z is equal to 2 column. You are dividing each of the entry in that column by that sum. So you are actually normalizing the probability values, right? Now this is a new probability distribution when you divide the each of the entries in that column by the probability that z is equal to 2. Z is equal to 2. So 1 over 16 you divided by 1 over 4, you get 1 over 4. The So this third entry is also 1 over 4. Second entry is 1 over 8 by 1 over 4, so it's half. And last entry is 0 by 1 over 4, which is 0. So now the sum of these is equal to 1, right? So you're actually dividing all these by some quantity such that the sum of those probabilities is equal to 1. So when the sum is equal to 1, that itself is a new probability distribution that you have, and you are finding the entropy of that probability distribution. Now, if we do that for other entries, you get 1/8 over 1/4, which is half. Then the third entry was also 1 over 16, which is a quarter, and the final entry was a 0. So now your entropy h of xy given z is equal to 2 is simply the probabilities multiplied by log of the reciprocal of the probability and added together. So it's 1 over 4 times log of 1 over 1 over 4, which is 4, plus half times log of 1 by 1 by 2, which is 2, and third entry is 1 by 4 log of 1 by 1 by 4, which is 4. Final entry is 0 times log of 1 over 0, but we define that to be equal to 0. So we only sum over the entries in the support, that is when the probability is not 0, so we ignore the final term, or we so there are two ways to look at it. One is while defining the entropy you can define only over the support. uh, that's what is done in our lecture, in our course, and in the notes by John L. Massey. In other textbooks, they just define that quantity to be equal to 0. So they define it, minus 0 log 0 is equal to 0. So the fourth term will be 0. In our course, the fourth term is not there because you're only summing over the support. Either way, you get half plus half, which is 3 over 2, which is option C. If you get a lot of practice doing it, you can just directly see uh, that since you have z is equal to 2, you're dealing with only the second column, and then since it's a conditional distribution, you have to just normalize this by dividing each of those entries by the sum of all the entries in that column. Then you take the entropy of that distribution. Was that clear? Okay. Question 8. So we are still dealing with the same joint distribution. For the joint distribution given in question 7, what is h of xy given z? Four options are 11 by 4, 13 by 8, 9 over 2, none of the above. So h of xy given z is by definition average over all values of z, at least those in the support, of, so since we are taking the average, you multiply by the probability of z of h of x given h of xy given z is equal to z. So we found this quantity for only one value of z. Now you have to find that for all four values of z, and then you have to find the probability that z is equal to small z for each value of small z, which is nothing but the sum of each column. So it's just a repetition of the procedure from question 7 for different values of z. So it will take a lot more time to do. I will give you the distribution and you can go back and verify that this is actually correct. So I won't write down all the steps, but I'll orally say it. When you're finding p of xy given z is equal to 1, this is equal to p of xy z equals 1 divided by p of z equals 1. What is the probability that z is equal to 1? It's the sum of entries in this column, which is 1 over 8 plus 1 over 16 plus 1 over 16 plus 1 over 4. So 1 by 16 plus 1 by 16 is 1 by 8. 1 by 8 plus 1 by 8 is 1 by 4. And then plus 1 by 4 is half. So probability that z is equal to 1 is half. And then you have p of xy, z is equal to 1. So we usually write this with this type of notation. Since xy can take four values, there are four probability values. We don't really care what the names are. So if this was 0, 1 and this was 0, 0, we don't really care. The distribution bar is the same. So since entropy depends only on the distribution, we'll just write out the four values that we get. So P of xy z is equal to 1 for xy is 0, 0 is nothing but P of 0, 0, 1 by P of half, which is 1 over 8 by half. So we are normalizing this first column by dividing each of those entries by half. So 1 over 8 by half is 1/4. 1 over 16 by half is 1/8, and 1/4 divided by half is a half. So that's the distribution P of xy given z equals 1. We already found P of xy given z is equal to 2. It was a quarter, a half, a quarter, and 0 from Q7. You could write P of xy given z equals 3 is P of xy z equals 3 divided by P of z equals 3. Probability that z is equal to 3 is 1 over 32 plus 1 over 32 plus 1 over 16, which is 1/8. And the distribution is 1 over 32 divided by 1 over 8, which is 1/4. Next entry is also 1/4. Third entry is 1 over 16, 16 by 1/8, which is a half. Final entry is 0 by 1/8, which is 0. Finally, P of xy given z equals 4 is P of xy z equals 4 divided by P of z equals 4. Sum of the entries in the fourth column is, so the third and fourth column are identical, 1 over 32, 1 over 32, and 1 over 16. So the distribution will also be identical. So this is again P of xy z equals 4 by 1/8, and you will get 1 over 4, 1 over 4, 1 over 2, 0. Now for each of these four distributions, this, this, and this, you have to find the entropy and take the average over all values of z. So h of xy given z is probability that z is equal to 1, which is half, into h of the first distribution, 1 over 4, 1 over 8, 1 over 8, half, plus probability that z is equal to 1, sorry, z equal to 1 is over z is equal to 2 was 1/4. So it's 1/4 entropy of the second distribution, 1/4, half, 1/4, 0, plus probability of z equals 3 and z equals 4 are both 1/8, 1/8 h of, and those distributions are 1 over 4, 1 over 4, half, and 0. Same for z is equal to 4. Now you can observe that the entries here and the entries here are the same, except that they are in a different order. But the ordering doesn't matter for entropy. So actually this and this are all the same number. Only this is different. So since these are all powers of 2, It's not difficult to find the entropies. Usually the notation is when you write it like this, you write parentheses like this. That's just the convention. So h of 1 over 4, 1 over 8, 1 over 8 half is 1 by 4 times log 4, which is half, plus 1 by 8 times log 8, which is 3 by 8, 3 by 8, and half log 2 is half. So it's 1 plus 6 over 8, which is 3 fourths, 1.75 bits. And the other three distributions have 2 quarters and a single half. So 1 over 4 log 4 is half, 1 over 2 log 2 is 1, 1 over 4 log 4 is half. This is 2 bits. Therefore, h of xy given z is half into 1.75 plus a quarter into 2 plus an eighth into 2 plus an eighth into 2. Or since the option was in terms of um, a fraction, we'll keep the answer in terms of a fraction. So we'll keep this as what is it now? 8 plus 14 over 8. Let's keep it as 14 over 8 or 7 fourths. So it is 7 over 8 plus 4 over 8 plus 2 over 8 plus 2 over 8. Unless I made a mistake somewhere. Let me check. Okay, sorry. This was also a half. 1 over 4 log 4 is 2 by 4 half. 1 over 2 log 2 is 1 by 2. That's also half. So this is actually not 3 bits, it's 3 by 2 bits because log 2 is 1 and half log 2 is half. So in all these places, we'll get 3 by 2 and then this will change to we can take an 8 common in the denominator. You'll get 7 plus 3 plus 3 over 2 plus 3 over 2. So this is nothing but 13. So the answer is 13 over 8. Did we have an option like that? Okay, option B is 13 over 8. So the answer is option B. Yeah. So in the definition, we had h of y given h of xy given z is summation pz of z times h of xy given z is equal to small z. So these z belongs to 1, 2, 3, 4. So I have this probability of z is equal to small z. That is the factor here. This is probability that z is equal to 1. This is the probability that z is equal to 2. This is the probability z is 3, and this is the probability that z is equal to 4. And that I have multiplied by h of xy given z is equal to, so this is h of xy given z is equal to 1. This is h of xy given z is equal to 2. This is h of xy given z is equal to 3, and this is h of xy given z is equal to 4. Is that clear? Yeah, so uh, this is just the way that we define it because we find this to be useful and it satisfies some nice properties if you write it like this. So at the end of the day, when you're writing h of xy given z or z is equal to small z, they all depend on the probabilities, and the probabilities are defined only for particular values. So you have the probability that x is equal to 0, y is equal to 0, uh, given z is equal to 2. You have this. There's no such thing as p of capital X capital Y given z. So the probabilities all depend on the values of small x, small y, small z that x, y, and z are actually realizing. So this means what is the entropy in x and y when you observe a random variable z and you observe that it has taken a particular value. What this means is that someone uh, says that I can give you the random variable z, but it doesn't say exactly what value it is taking. Right? But just by knowing that someone will give you the random variable z, the uncertainty changes in x and y. So you have to average over all possible values that your z value can take. So, for example, if there is an experiment, and on that experiment you have defined three random variables x, y, and z, each can take different values. Now you conduct that experiment once and you get some particular value for z, and I give you the value of z, then you are asked, but you don't know what x and y are. I only give you z. Then you have to find out the uncertainty in x and y while knowing that some particular z value has occurred. That is h of xy given z is equal to small z. But suppose I conduct this experiment many times, say n number of times, where n is going to infinity. So you keep conducting that experiment. Then each time the value of z is different, right? So for each of them, you'll have h of xy given z is equal to z will keep varying. So on average, what is the value that what is the uncertainty in x and y, given that you know z. So you know that z will, someone will tell you the value of z, but z itself is a random variable which varies with each experiment. So you are trying to capture that information, the information that z is a random variable. And sometimes, if the distribution of z is not uniform, then a particular value of capital Z can occur more number of times than the other values. So h of xy given, for example, here p of z is equal to 1 is half, but p of z is equal to 2 was on 3 was only 1/8. So if someone gives you the value of z each time, when you conduct a large number of experiments, on average, what is the uncertainty you can uh, get by observing z? That depends on what value of h of xy given z will take for different values of z. So you can think of h of xy given z is equal to z as conducting the experiment once, finding out the value of z, and once you know the value of z, what is the uncertainty remaining in h of x and y? When you say h of xy given z, the random variable z, that means if you conduct a large number of experiments, and in each experiment someone tells you the value of z, but that z value itself occurs with different frequencies. So some of these z values can occur more number of times and some can occur less number of times. So whichever value occurs a lot of times, that will influence the uncertainty in x and y more, and whichever value of z occurs less number of times, the uncertainty associated with that in the sum will occur less. So you have to take an average over all possible values of z. So that's why we have that pz of z term. It's an average over all values of z. And in this problem, pz of z is half, one fourth, 1/8, and 1/8. Next, we have next two more questions, and these are conceptual questions. There's no calculations involved. Which of the following is a convex function? And the options are log x belongs to 0 to infinity, I of xy as a function of p of x for a fixed p of y given x. Option C is I of xy as a function of p of y given x for a fixed p of x. Option D is h of p as a function of p, which is a binary entropy function. So we can easily rule out option A and D. A is the log function. Log function. This is a concave function. D also is a concave function of this one. So for B and C, we don't really have direct curves, but using Jensen's inequality, I think it was proven that as a function of P of y given x for a fixed P of x, I of xy is convex. So correct answer is option C. I think it should have been proved after as a consequence of Jensen's inequality in your lecture video. So basically here P of xy P of xy can be written as P of x times P of y given x. So if you fix one of these and vary the other, then you're varying P of xy. Uh, if you fix P of y given x and vary P of x, then also you're varying P of xy. So since you're varying P of xy, I of xy, which is defined as h of x minus h of x given y, that will also vary according to a certain pattern. Then you have to analyze both h of x and h of x given y and see if they are convex or concave. Analysis should have been done in class. Then you'll find out uh, whether I is convex or concave. There's no problem in this question, right? I'll go to the next question. Let x hat be an estimator of an Emery random variable x. That just means it has x takes m values. Which of the following statement is true? This can previous thing is a consequence of Jensen's inequality. So the options are P of x not equal to x hat is greater than or equal to h of x given x hat minus 1 by log of m minus 1. P of x not equal to x hat greater than or equal to h of x given x hat plus 1 by log of m minus 1. And C is P of x not equal to x hat greater than or equal to h of x given x hat plus log m. D is none of the above. Solution for that is just option A. Uh, that's because let's say let PE be equal to probably that x not equal to x hat. From Fanos lemma, you have h of PE plus PE log of m minus 1 must be greater than or equal to h of x given x hat. So let E be the event, E be the random variable with which takes the value 1 with probability PE. So it takes the value 1 when x not equal to x hat. It takes the value 0 when x is equal to x hat, and that occurs with probability 1 minus PE. Then h of E, the entropy of this is h of the binary entropy function, h of PE, which is less than or equal to 1. From that we get h of x given x hat less than or equal to 1 plus PE log of m minus 1. So PE log of m minus 1 is greater than or equal to h of x given x hat minus 1. That means P is greater than or equal to h of x given x hat minus 1 divided by log of m minus 1. So this follows from the Fanos lemma, and Fanos lemma must have been done in lecture 3 or something. So if you have any doubt in Fanos lemma or Jensen's inequality, you can ask. Otherwise, that's it for today's problem solving session. Yeah. Any question? The notes, I think it will be shared with you guys, so you don't really need to write it down. Okay, if there are no questions, then I'll end today's session. We'll see you in next week's session. Next week should be week 2 content must have been released. It's on coding, block coding, I think, block to variable length coding, Huffman coding or something. So we'll meet next Saturday. Thank you for attending and bye bye. Good night.